vamos a dar la palabra al doctor Bashbush, quien nos dará nuestra bienvenida para este foro internacional. Doctor, le escuchamos. Su micrófono aún está apagado, doctor.
Can you hear me now?
Sí, doctor. Thank you. We hear you now.
On behalf of the SPE, and in particular on the SPE Mexico section of the Association of the Young Professionals, I want to highly thank our distinguished presenters for having agreed to participate in the forum and to share their experience with us. Thank you very much. We are really looking forward to listening to your presentations and to the discussions. And again, we want to thank you for your kindness in sharing your knowledge. Thank you very much. Ms. Hannah Tufayli, Mr. Harshil Saradva, and Mr. Luis Castellanos. Thank you very much for your participation, and we are grateful for that. Básicamente, les dimos las gracias a los presentadores y con eso nuevamente cedo la palabra a quien está dirigiendo esta sesión. Muy buenos días a todos y gracias por participar.
Doctor, muchas gracias. Siempre es un gusto contar con sus palabras y sobre todo que pueda darnos la bienvenida a este evento. Es un privilegio. La sesión será en el idioma inglés, así que a partir de este momento vamos a cambiar a ello para poder también tener en cuenta a nuestros participantes internacionales. I'm now presenting the agenda that we have programmed for today. As you already saw, we had the introduction and the opening words by our dear friend Bashbush. As a third item on the list, we're going to have the lecture, Integrated Field Development Planning for Enhanced Condensate Recovery and Gas Storage in Mature Gas Condensing Fields by Harshil Saradva, who is representing the United Arab Emirates of the SPE. Following that, we're going to have Hannah Tfaili from the Italian SPE section, and she will be delivering the topic, Carbonate Karstified Oil Fields 3D Modeling through Equivalent Relative Permeability Curves. Last but not least, of course, we're going to have Luis Castellanos Basul, who is representing Mexico Section SPE, and he will deliver the topic, Application of Artificial Intelligence to Seismic Petrophysical Modeling, the Benefits and the Risks. My apologies for that. Afterwards, we're going to have a question and answer session. But this will be at the end of the three conferences. So please, if you have any questions throughout the delivery of them, feel free to write them on the section, on the chat of this video conference, either in Spanish or in English, and we will ask them at the end of the program. Each participant will have 15 minutes for sharing their presentations, and you are welcome to take notes, and as I mentioned at the beginning, this session will be recorded. If you would like to follow with more detail along the conversation that we're going to be having, you can activate these options on your screen. As you can see on the top right side of your screen, there will be the section More or Más. And if you click on Activar subtítulos en directo, then you'll be able to follow the conversation and what is being said in English. Please do note that this is not a translation, it's a transcription. So you will only see the written notes on the spoken language. With that, and with no further delay, I'd like to introduce Harshil Saradva. He is a bachelor in petroleum engineering technology, but also has a master's in petroleum engineering from the Heriot-Watt University in Dubai. During his student years, he actually was a semifinalist at the 2015 Petropol Regional Qualifiers in Bahrain. As for his professional experience, he is a reservoir engineer and is working with Sharjah National Oil Corporation in the United Arab Emirates. His experience is in field development planning, reservoir monitoring, reservoir simulation, well intervention planning, PVT testing of fluids, and well testings. He specializes in simulation runs, management of gas storage projects for peak performance, and reservoir management of producing fields. He's the author of the reservoir engineering section of the field development plan that comprises well test summary, reservoir simulation scenarios, and upcoming field development plans for the newly discovered fields. He has mentored, which must be a privilege, and guided 9 petroleum engineers, undergraduates, and postgraduates with their theses and projects. Of course, he's an active member of the Society of Petroleum Engineers, and he will be giving us the lecture Integrated Field Development Planning for Enhanced Condensate Recovery and Gas Storage in Mature Gas Condensate Fields. Harshil, you have all our attention, and thank you again for giving us this part of your knowledge.
Thank you, Maria. Thank you for that kind and extensive introduction. Um, and thank you everyone for having me here as well. It's our pleasure and my honor to be presenting what we have done in the past, what we strive to do in the future, and basically also be open for your comments and your insights into our activities as well. So with that, I will now share my screen, and I will proceed with the presentation that we have. Please let me know, Maria, if you can see my screen.
Yeah, we see it and we hear you.
Okay, perfect. Thank you. Great. Thank you, everyone. So the presentation or the topic that I will be discussing on today would be on integrated field development planning for enhanced condensate recovery, so ECR, and gas storage in mature gas condensate fields. So we have our co-authors who will be also attending the call as well. So we have this presentation which was made for ADIPEC in 2018. So that is the Abu Dhabi International Petroleum Conference and Exhibition. And I have with me Siddharth Jain, Mark Sarsam, Masood Al-Hamadi, and Matthew Robert, who were co-authors with us on the task and also the paper itself. Right, jumping in. So I will be following this outline for the presentation today. So we'll just brief you in with the introduction, what the field is, and where it is located, and what sort of parameters do we have. Then I will go deeper into the challenges that we have faced or the limitations that we have in terms of our own field and the data set. Then I will discuss on one of the pilot injection projects that we did for this field. And this was done in 2017, and we have taken it a step further, which I will be discussing along the way. And then I will be discussing something more on the composition simulations that we have run on this reservoir itself, and the conclusions and the way forward. And that would be it from my presentation at that point. Right, so if you look on the graph on the right side on the figure, we have Sharjah, which is highlighted in blue. So that is the Emirate of Sharjah within the UAE itself. And we have the field in discussion here in green color. So it is basically an onshore field. And it is located very well within Sharjah itself. And it's further away a bit on the outskirts of the city. So it's like 30 kilometers, half an hour drive from the city. It's very convenient. And moving on. All right, so introduction of the reservoir. What do we have? We have a field which is mature. It is rich gas condensate, and with the CGRs which go up to around 100 to 120 STBs per million SCF. And this field was developed in 1982. So the first discovery of the field, or the exploration well discovery that we had, was in 1982. And since then, the field has been on production. It was ramped up much further in 93 or 92, where we had X3 and X4, which were brought online on production. And then we went on producing with a few additional wells in the field. So these X5 and X6 came online in 1995 and 1996. So the said field is basically over, let's say, 40 years now. And it has been going strong at that point. And at the time of this presentation, the field was in depletion drive. So we were producing from the wells, and through the history of the reservoir itself, there was no gas reinjection done. There was no sort of pressure maintenance, and there was so basically what was the strategy that was undertaken was just produce the field, capture what we can, and then process the gas or the condensate that we recover along with it. So at that point, we had around 95% gas in place, which was already produced. However, we had left behind 50% of condensate in place. So on a field of this size, that 50% amounts to a lot of money, and it's also a lot of reserves in the well, that in the reservoir, that has been basically lost forever. But we wanted to try to go and capture this and as much as we can. So what we did was to understand how the field was behaving and see what was happening. We then therefore went and created, or let's say, single and dual porosity models. So this exercise was undertaken because we did not have any legacy data sets. So in terms of operatorship, the field was discovered by the international oil companies back in the date that I mentioned, and then it was handed over to SNOC as the operatorship in 2015. So that's when SNOC got the full handle on the field, and then we were able to take our own decisions and dive deeper further into proper reservoir management. And that's where we started making models, and then we had devised further exercises on how to improve what we have. And therefore, once we had the models, we had the simulation results, and then we knew what would happen if we go and do some gas injection in the field. So our primary objective was to have some gas storage, because we wanted some strategic stronghold on the gas supplies that we have within the Emirate of Sharjah. And as a secondary objective was to also have enhanced condensate recovery. So this was the pilot project's let's say the agenda or the objective. All right, so the challenges that we faced. So static modeling was, we'll start off with that aspect of modeling itself. So rock typing. The issue that we face with rock typing is, if we look at the graph which we have here in the center, so the rock typing is nomenclatured in this way. So the blue one is RT1, the red dots are RT2, so rock type 2. The triangles in green are rock type 3, and the X's are rock type 4, and then the rest is rock type 5. So if you look at the scale here, we see the higher quality or the good quality rock type 1 is, it varies in terms of permeability from, let's say, around 0.2 to around 10. So this is on a log, semi-log scale. So this is log, and that is Cartesian. And then we have, we can observe that as the rock type deteriorates, that means as the core porosities reduce, the deviation or the permeabilities that we have is far too much, right? So it goes from very low to very high, sometimes to the order of rock type 5 goes up to the order of 2 times. So this is happening because we have something called microfractures within the reservoir, and this reservoir is carbonates, which I forgot to mention in the initial slides. So it's not sandstone, it's carbonates. And so we have something called naturally occurring microfractures, and therefore we have this sort of behavior where it varies a lot within the same core porosity ranges. So that was one of the rock typing issues that we have, challenges. And the second one was composition versus depth. Now our reservoir thickness is let's say 2,000 feet, right? So we cannot have same composition which is applicable through the whole section of the reservoir, and especially because the geothermal gradient changes and or the temperature changes with depth, and therefore the composition of the hydrocarbons change, which is located there. So we had to implement something called compositional change with depth. So that's for reservoir simulation experts here. That's the ZMFVD keyword that we had to implement. And we used the RFT data sets that we had, and we tried to get a match on the compositional change based on, we figured out the geothermal gradient first, and then we made the compositional change. So we implemented this change in the PVT model itself. And the next one was PVT, because back in 1980s or early 1990s, when the well was, or the field was recently discovered, we did not have access to what we today enjoy in terms of luxury, is the single phase water mole sampling. It's very crucial for gas condensates to be sampled in such a way, because we cannot trust, or the extent of uncertainty that we have in surface well testing is quite a lot. So when you go and collect your liquids and gas at the surface separator, you don't know for 100% surety that are those numbers guaranteed that it's exactly what they represent. So in terms of recombining these fluids and then performing the analysis of CCEs and CVDs, this will be you will have an inherent uncertainty. So we did not have this luxury, and therefore, since these samples were recombined at the surface, and the drawdown which was required to achieve this production rate was much higher. So the well was already below the dew point pressure. So we were not able to trust our numbers in terms of PVT. That's why PVT was one of the other challenges that we had with static modeling, at least. Moving on to dynamic, what we have is you see that Petrel, or E300 for that matter, it uses the sales gas headers for your regression. So you could either use gas or oil for your matching parameters with your observed data set, but we use sales gas. And that readings were, however, taken at inlet separator conditions. So inlet separators, and that's why we were not able to capture the second stage gas evolution. So whatever was produced from the second stage was not captured in the simulator as well. And that's why what we did was we had to implement engineering assumptions, made some technical assumptions which were sound enough, and then we tried to go on with what we had best available at that point. We did a pilot injection, so that was phase 1 and phase 2 basically. And what we did was inject in 3 of the wells. We injected 1,000 psi, and we tried to see what the wells were injecting in terms of volumes and rates. And the average injection rate that we observed was around 27 to 30 when 3 of the wells were injecting. And another 3 wells had gauges installed. So what we were doing is in the offset wells, we were, or in the observer wells, we were capturing the bottom hole pressure changes on a very micro scale, and we wanted to see, do they see any pressure fluctuations when we go and inject in the nearby wells. So the objective of this whole exercise was to determine the well injectivity, determine the well intercommunication, and also to determine if the condensate revaporizes, and also to check the wellbore reservoir parameters. So we were measuring the fall-off and the PBU. We recorded the fall-offs and PBUs, and then we did the PT analysis on it. Right. And pilot injection again. So we have the graphs from one of the wells. So that's well X1. And we see that this is the pressure which was going down. But if you see the magnitude, it's very, very small. So one minor grid line here is around 0.2 of a PSI. And we injected certain volume here, and we do see minor slope change. It's not very explicit as you see in the next graph. So we start injecting here, and the pressure response is it's right away. You can see that there has been some sort of contribution or communication between both the wells. Right, and there was so we have results from X1 and X6, and X5 was the results were not very beneficial because it was showing the well under a PBU. So given that that was masked, so we basically say that the results from X5 were not valid basically. So what happened when we produced these wells? When we started the wells on production, we see that we were able to gain the compositions that we had injected earlier. So the graph here, what it represents is the fraction of the composition that is produced now to the composition that was originally present in the reservoir before injection. So as the graph or the trends move towards 1, what it means is that you are now achieving your original compositions that you already had. So we injected lean gas, so that's basically 95% of methane. So once you injected 95% of methane and you start production, what we gain is methane that is basically the methane, and then it starts to pick up those heavier condensates. So C3 and the LPG, C3, C4, C5 plus the condensate starts picking up. So you can see that from the graph here. And these are 2 wells. What we want to show from this graph is basically that the higher producer or the injector is able to recover those fractions to 1 much quicker. So this well was able to do this in like 25 days. The other one took around 60 or 50 days to achieve even half of those numbers at that point. But the better the producer it is, the quicker it will attain those initial reservoir compositions. And if this would have continued, we might have been able to see the revaporization of the condensate at that point. So the reservoir simulation, what we have is two different models. One was single porosity and dual porosity. And we have the parameters here. So basically all the same. The dual porosity was having more number of cells, and we have used both these in our simulations going forward. And I won't explain this in much detail, but the gist of the whole story is that the huff and puff, you see that the condensate is much higher initially, and then it starts declining with time. Because what it does is it tries to pick up the condensate which is nearby, but it's not able to pick up the condensate which is further away from the well, especially if it's the equal duration shut-in and production periods. And on the other hand, if you have sweep on a dual porosity model, which is the green in color, it picks up the condensate, and the cycle is very stable, and therefore it basically gives you an idea on the difference on the quantum of results that you gain between a single porosity and a dual porosity model. So one has to be aware on what sort of reservoir or the rock that they have in the reservoir itself. So if it's microfractures, or do you think you have fractures, or if it's just single porosity behavior, it's very important that we capture this, and because your results would be very different and your strategy would be very different going forward. Now, conclusions and way forward. So what we did with this exercise was we took a very mature field, which was basically at the end of its reservoir life. And what we have done is we went and tried a theory where we see if we can inject, is it a good reservoir to be a gas storage field? Basically to figure out can it hold the pressure, and if it can, then does injecting give us any further benefits? Like does the condensate revaporize? Are we able to extend our recoveries further than the existing recovery percentages? And then going forward, what we plan in doing this, because we saw positive outcomes, was to implement 3000 psi capacities, which we already did last year. So from the last 4 years, so since the presentation was initially published on public domain, we have increased our injection capacities, and we are now in a position where in the near future we would start gas cycling again. And in order to also improve the condensate recoveries, we have something called UBCTD, so that's underbalanced coil tubing drilling, and which we plan to implement in the reservoir itself. So next year we will be doing that. And what this gives us, because this again is part of a published paper, so we have this applied on our other fields. So this was done in early 2000s, and in that field it has around 170 laterals in many of the wells. So it's a multilateral network of mesh which improves your well's connectivity with the reservoir drastically. So you can then tap into the condensate which is dropped out further away from the wellbores itself. And basically what we also want to highlight, and what we think and what we also know now, is that this is a long-term project. It's not like you would implement something now and you will see the results or the benefits of condensate recovery in like 2 years. It's a long-term agenda. It's a long-term project. So a few decades, or at least a decade, and obviously this depends with the reservoir that we have and the wells and the connectivity and everything. But it's a long-term project. It's not immediate action that you will see on your reservoirs. And to develop going forward is to develop a dual porosity and dual permeability model, and we want to test its compatibility as well. Because right now what we did was just single porosity and dual porosity, and we saw that the results were quite different between each other and quite counterintuitive. So going forward, we want to test out the DP-DP model that we call it, and we want to see how are the results compared to the other two that we have already done. And we will take further into the results uncertainty. So we want to re-optimize what we have done. So the rock types that we have a rock type study ongoing, and we're trying to reduce those uncertainties in whichever extent possible, so that we know whatever simulation results that we get are as accurate as possible. And we also want to incorporate some sort of economic analysis, a brief economic analysis from an engineer's perspective, see how much gas do we inject for your cushion gas, how much more additional funds do you need to drill the wells, and also what sort of returns will we gain out of doing such exercise. And we have run simulations with CO2 and nitrogen, and we have our own results as well. However, we want to take this study further and see how the recoveries would change when you go and change your sort of gas that you have that is being injected. You could have either only one gas being injected, it could be pure methane, or you could alternate between two immiscible gases. So you could have CO2, and then you could also have, let's say, a spacer between, and then you can have methane along with it. So it's a different mixture that we could have to investigate and see going forward how it behaves. So I believe that would be all from my side. I had to, this is a very extensive paper. I would recommend that you, if you're interested, you could go and download it from the One Petro, and you could see that the data over there is much extensive to this presentation anyways. Last but not the least, thank you everyone for your time. Sorry if I went over by 3-4 minutes over here, but and I would also like to thank Sharjah National Corporation for giving us this wonderful opportunity and the data set to present to young engineers, young professionals like us of the SPE section, and everyone else joining us from around the world. And obviously, the highest appreciations for my co-authors and colleagues who have given their valuable assistance, their valuable insights. Not something that we have done before, in the sense that this is basically writing like a new book. That's why brainstorming and any ideas were welcome, and they were tried and implemented. And this is a success that we enjoy today from our side. Thank you for your time. That will be all from my side.
Harshal, thank you. That was quite insightful. And no doubt the idea, the concept of having revaporization of condensate within the reservoir is quite a benefit, something that we should all consider doing if that is the reward. So we're going to leave the questions for the end of the rest of the program. Les recordamos que las preguntas las pueden incluir en la sección de chat y las vamos a tener al final de las 3 presentaciones. Meanwhile, in between, on behalf of the SPE Mexico section president, that is Francisco Javier Flamenco Lopez, we want to acknowledge and sincerely thank your presentation, the time and the effort that you have put into collaborating with us today. So please virtually receive this acknowledgement. We are going to send it to you through email, but we're quite happy and very honored to have you here.
Well, honor is all mine as well, and all the pleasure as well. Thank you, Maria, and everyone.
Thank you. Okay, so now we're going to move on with the next lecture, with the next presentation. We're going to have Hannah Faidi. Before she starts, I want to introduce her to you. She has a bachelor degree in petrochemical engineering from the Lebanese University in Beirut, and also a master's degree in petroleum engineering from the Polytechnic Institute of Turin. Back in her student days, just as Harshal, she was also a second place winner along with her teammates at the 2016 Petropol. As her professional experience, she works as a reservoir engineer at Eni, and her current work includes production data analysis and history matching of giant reservoirs. Sorry. She specializes in field development, strategies, and risk analysis, and elaborated the thesis Reservoir Uncertainties Risk Analysis and History Matching using the Ensemble Smoother Multiple Data Simulation. She published the article Carbonate Karstified Oil Fields Geological Prediction and Dynamic Simulation through Equivalent Relative Permeability Curves that you can download at the SPE One Petro website. Of course, she's also an active member of the Society of Petroleum Engineers and of EAGE. She will be presenting the topic Carbonate Karstified Oil Fields 3D Modeling through Equivalent Relative Permeability Curves. Hannah, you have all our attention. Thank you.
Thank you, Maria, for this kind presentation, and thank you all for being here today. So I'm going to share my screen. Let me know if you can see it.
We see it now.
Okay, great. So thank you for this presentation, and thank you, Harshil, for the very nice presentation that you have shown previously. Well, today I'm going to present a little bit of a different topic about carbonates. I'm going to talk about karstified carbonate fields. And specifically, I'm going to show you a methodology that we have developed here in ENI in order to match water flooding in a karstified oil field. Well, the work was done by my colleagues named here and myself, and I have reported the number of the paper and its title if you'd like to download it. Well, the agenda for tonight is subdivided as follows. I'm going to show you, first of all, the scope of work. I'll show you different approaches for karst modeling. Then we will see an equivalent representation of through pseudo-relative permeability curves. And finally, I will introduce the case study. And of course, we will finish with the conclusions. So as I mentioned previously, the main scope of this work was to identify a simple method that allows to predict and to replicate as simple as possible water flow in a karstified porous medium by using a single porosity model. And luckily, we had the chance to apply the developed methodology to the history match of a Middle East field. And the results were quite promising and were successful. Before going through the presentation, let me just give you a very brief refresh and reminder of karst. Well, karst is a feature of tropical carbonate reservoirs, and it manifests as the dissolution of calcium carbonate by water, by the carbonic acid, so carbon dioxide dissolved into water. From a geological point of view, it results in the formation of holes, vugs, channels of different sizes and different geometries. So it leads to a very big heterogeneity in our reservoir. So let's say that modeling it is quite challenging, just as modeling any carbonate reservoir, actually. So what are the approaches for karst modeling? On a macro scale, let's say there are two possible approaches in order to simulate karst. Whether we simulate at a very fine scale, so we go down to a very small size as the karst itself, horizontally speaking. And here I'm talking about cells sized 1 by 1 meter or 10 by 10 meters, which means that we have to increase by a lot the number of cells. This is actually quite a big problem because, first of all, we require longer computational times and higher computational power. It's not a very big problem here in ENI since we have supercalculators. However, increasing the number of cells increases the uncertainty in predicting the exact karst location. So we have more cells and we have higher uncertainty in predicting where is karst located exactly. The alternative approach could be the tuning and the adjustment of relative permeability curves. Let me just put the pointer here. Okay. So this is the approach that we have adopted in this analysis. To do so, we started with a synthetic model. So we considered a coarse cell sized 100 by 100 meters. And we transformed it into a fine scale model. So we subdivided this 100 by 100 meter cell into 100 smaller cells, each size 10 by 10 meters, as you can see here. Within this coarse cell or a block, let's call it block, we identified two different media. The matrix medium shown in blue with a permeability of 20 millidarcies, a porosity of 10%, and with which we associated the Corey-like matrix relative permeability curves, so the typical relative permeability curves. And we identified a different medium, which is the karst channel, here shown in red, with a permeability of 200 millidarcies, a porosity of 15%, and with which we associated the crust-like relative permeability curves, which are typical of fractures or enhanced permeability phenomena. Here we have reported different, let's say, configurations of karst just to remind you of its heterogeneity and its randomness. However, for the sake of simplicity and for the sake of this exercise, we considered a rectilinear channel crossing the block from one side to another. We placed 10 different injectors on one side, 10 different producers on the other side, and we consider constant injection rate at the same date, starting constantly in time. So what happens in terms of simulation at a fine scale model? The results are shown in here. As you can see, as expected, actually, that the karst channel is flooded straight away by water, and already at step number 4, you can see that we have here an 87% of water cut at the producer at the other end of the karstified channel. We have, of course, lower water advancement in the remaining part of the matrix. However, if you look at the oil saturation, you can see that even at the last simulation step, the saturation of oil in the entire block remains quite high. So what's happening here is actually a very fast movement of water, and the sweeping, let's say, of oil is quite inefficient. So we have an important amount of oil left behind. So this is the result that is obtained by using a fine-scale model. The scope of this work was to develop an alternative approach that allows to obtain the same identical result by using a coarse-scale model. So here we start to talk about the pseudo-relative permeability curves. In order to move from the fine to the coarse-scale model, of course, we started by the upscaling of absolute permeability and porosity, by using the weighted arithmetic average. So we've calculated, first of all, these two petrophysical properties. And then the only remaining unknown in this case was the relative permeability to water of the entire block. Well, we know that the total flow rate across the block is nothing but the summation of the single flow rates across each single row. So QW total is equal to the summation of QWJs. We're considering here a laminar flow, and we apply Darcy. So we replace simply the Darcy equation by the flow rate, but it's by equivalent Darcy equation. So we have here the equality that you see here. Delta P is constant across the block. We're talking about the same delta X. We could simplify constant terms, and we're left with the equality in here. Well, all the parameters that you see in the equation here are known except for the average relative permeability to water of the entire block. By rewriting this equation and by combining it with the average water saturation that is calculated as the weighted average by accounting for cell porosity and cell height, we were able to construct and to build the corresponding pseudo-relative permeability curve. As you can see here, it has this very particular shape. It is convex. We're talking about a very fast ramp up of water at the beginning of water flood, and already at small values of water saturation, you can see that water overcomes oil. So theoretically, we're seeing the same behavior that we have observed with the simulation at a fine scale. So in order to test and to validate this method, we performed 3 different scenarios, actually 4 different scenarios. The first one is the one that I have shown you previously, so the simulation at a fine model. And on the opposite side, we've simulated the 3 different cases by using the coarse model. So here we're talking about upscale porosities and permeability. In the first case model, we used the pseudo-relative permeability curves that we have calculated just now. The second one, we used the cross-like relative permeability curves. And in the last one, we used the Corey-like relative permeability curves. So from a simulation point of view, these were the results that we have obtained. As you can see here, well, let me just remind you of all the simulation cases. The black dotted line shows the results obtained with the fine simulation case. So it is, let's say, the ideal case we would like to have, but it's not practical. So it's the one that we would like to match from this synthetic exercise. The three continuous lines in here show the results obtained with the upscaled model. The red line shows the result using the pseudo-relative permeability curve. The blue and the green lines respectively show the results obtained by using respectively the straight line Caparel and the matrix KREL. You can see clearly that both the green and blue lines have delayed water breakthrough timings and have unmatched water cut trends and have unmatched also water production volumes. Also in terms of oil production, we don't see a match in this on this matter. Here as well, we have reported the plot of the water cut versus oil cumulative, and you can see that in all three cases, the best match is obtained from using the case with the pseudo-relative permeability curves. So this is from a synthetic point of view. What we've done in reality was actually an application to a real case study in the Middle East. Let me introduce briefly the field and the reservoir we're talking about here. So we're located in the Middle East. We're talking about a giant, 60 kilometers by 15 kilometers. And mainly this reservoir is a carbonatic reservoir, and it is subdivided in 3 levels. The upper one is highly karstified, and it is characterized by permeability enhancement phenomena. Recently, we started seeing water production in the field. It is a very old field, so recently we started seeing water production increasing, and during the process of the update of the reservoir model, the first thing that we've done was to update the methodology adopted for karst prediction and karst modeling. So in order to update karst prediction, a supervised neural network model was followed, a data-driven model was followed based on all hard data from PLTs and well tests, image logs, core data, and more importantly, 3D seismic attributes in order to drive and to conclude karst permeability distribution volumes and in order to, let's say, predict the possibility or not of the presence of karst. One of the outcomes of this analysis, for which I actually reported at the end of the presentation, the references and the publications. One of the outcomes was this property that you see in here, the so-called karst flag property, which is a discrete property, where the red color or the 1 value shows the high probability of karst presence, and the gray color or the 0 value shows a low probability of karst presence. The geological model itself accounted for this karst flag during the distribution of permeability enhancement. So whenever we didn't have hard data of the presence of permeability enhancement, so we didn't have a well test that showed us permeability enhancement, the geological model used the karst flag in order to apply absolute permeability enhancement. So what happened when we simulated the geological model as it is? As you can see here, we were far from matching water production at field level, and I ensure you were also far from matching it at well level. This was actually the same problem that was seen also in the previous model, yet the geological model has accounted for the permeability enhancement due to karst. So what we've done from a dynamic point of view was to reconsider the evaluation of saturation functions. Mainly, the reservoir model had 3 different saturation functions that used matrix relative permeability curves derived from lab analysis. Of course, we didn't have any relative permeability curve from lab analysis for the karst, since all karst samples arrive destroyed to the lab. So we didn't have any lab indication on this matter. What we've done here was to introduce an additional saturation function, or the so-called satnum. And this additional satnum, shown here in red, corresponds perfectly to the karst flag equals to 1. So when we have high probability of karst, we have added an additional satnum number 4. And we correlated, we associated to this additional satnum a pseudo-relative permeability curve that was tailored for this field specifically. What happened here in terms of simulation? Well, you can see that we moved from the blue line to the red line in here. We improved water production by almost 60%. Of course, this was not enough in order to achieve the history match. We had to perform other adjustments geologically and dynamically further on. However, this improvement was observed not only at at field level, but also at well level. If you check on the paper, you can see also several examples. However, here for the sake of time, I didn't report everything. So let's say that this approach was quite promising and was quite interesting during the history match of this karstified oil field in the Middle East. I hope I didn't run out of time. I have just reached the conclusions. So mainly here in this specific case, since we have a two-phase flow, it was necessary to modify and to upscale the relative permeability curves in order to simulate water flow within a karstified medium, a medium with such a contrast of porosity and permeability, actually of permeability. So the relative permeability curves have proved to be a very good tool on this behalf. And luckily, we had promising results during the history match of a Middle East field. This approach is quite easy to compute. It could be applied also using automated spreadsheets. And finally, it works just fine also for other diagenetic systems, just like Rudis, for example. And that's it from my side. As I told you, I have reported here the references about karst prediction and also about the pseudo-relative permeability curves if you're interested in this topic. And thank you so much for your attention and for your time. And thank you all for the organization. And yeah, that's it.
Hannah, thank you for the time you put into this. I appreciate that. And we see that's quite an interesting topic, not something that we hear very often. So that's good. It's good to see that for a change. Thank you. Well, as I mentioned before, we're going to have the question and answer session at the end of the whole program. So please feel free to write them on the chat of this video conference. Recuerden que pueden escribir sus preguntas en la sección del chat que está aquí. Puede ser en inglés o en español y al final del programa vamos a hacerlas. Now, on behalf of... oh, okay. Sorry. My computer it was not clicking. Okay, we want to thank you. And also we want to acknowledge the participation, the effort, the time you put into this. And please receive this acknowledgement, receive our thanks for developing this topic. We know it's a lot of time. We know there's a time difference, so we're very grateful. And well, congratulations, and we really hope to have you again in our future programs.
Thank you so much. Pleasure is mine.
Thank you. Okay, so now we're going to move on and we're going to have our last presenter, our last lecturer, and he is Luis Aindel Castellanos. He's a petroleum engineer from the National Autonomous Mexican University, or UNAM, and has a master's degree in educational sciences. He currently works at Pemex as a technical specialist for the exploitation plants management based in Villahermosa in Mexico. He is a seismic petrophysic with over 7 years of experience and specializes in identifying business opportunities, optimization of processes, and maximizing the profitability of the projects he's into. He also is in charge of generating and validating the petrophysics and rock physics models for the conventional and unconventional resources we deal with every day. He plans, organizes, and leads closure for specific projects within budget and scope, of course, and has also published a paper on the SPE, and this is static analysis in petrophysical model, field and case of success in case hole completions. And you can consult this on the Petro website, on the One Petro website, sorry, under the number SPE 1991-39/MS. Of course, he's an active member of the SPE, but also belongs to other associations, local associations such as the AIPM and the CIPM. He will be presenting the lecture Application of Artificial Intelligence to Seismic Petrophysical Modeling, the Benefits and the Risk. Luis Aindel, you have all our attention. Thank you.
Thank you, Maria.
You can start sharing your screen now. We see it now.
Okay, thank you, Maria. I'm going to talk about an application of artificial intelligence, AI, to seismic petrophysical modeling, benefit and risks, which was developed with data. Okay, this will be what we will see in the following minutes. We have the petrophysics and artificial intelligence, seismic petrophysics, rock physics model, or case review, and finally the conclusion. These works discuss the interaction between rock physics models and artificial intelligence and how we have implemented the reconstruction of S-velocity to found natural fractures. We will show you the equation and concepts behind the theory using graphical and probabilistic methods. Perhaps the easiest way to think about an artificial intelligence, machine learning, neural networks, and deep learning is to think of them like Matrushka dolls. Each is essentially a component of the prior term. That is, machine learning is a subfile of artificial intelligence. Deep learning is a subfile of machine learning. And neural networks make up the backbone of deep learning algorithms. In fact, it is the number of node layers or depth or natural network that distinguish a single neural network from a deep learning algorithm. After that, we must to know a neural what a neural network is. So, in a simple word, a neural network is a matrix and is a mathematical analysis. The input layer of neurons or nodes represent the input x and the number of neurons in the dimension of the input x. The output layers represent the output y and the number of the neurons depend of the nature of the target variable. For regression and binary classification, it's only one. For multi-class classification, the number of neurons is the number of classes. So in this part, we have an example of neural network working, but what do all the colors mean? Orange and blue are used through the visualization in slightly different ways, but in general, orange shows negative values, while blue shows positive values. The data point represented by small circles are initially colored orange or blue, which correspond to +1 and -1. In the hidden layers, the lines are colored by the weights of the connection between neurons. Blue show positive weights, which means the network is using the output of the neuron as given. And orange lines show that the network is assessing a negative weight. In the output layer, the dots are colored orange or blue depending on their original values. The background color shows what the network is predicting for a particular area. The goal of artificial intelligence is to mimic the human brain and create systems that can function intelligently and independently. Uh, One of the main problems within the petrophysical workflow is the detection of anomalies in the data. For this, we have developed different workflows that help us to find these inconsistencies in the data. For example, we have isolation forest, also outlier factor, and one class SVM. The isolation forest, the method is based upon decision trees. The outlier factor, this method assesses the density of data points around a given point. And finally, the one class SVM, the support vector machines are a common machine learning tool for classification, which means they are good for splitting data up to into different groups based on the data characteristics. So we must to have effectiveness of outlier detections. In this slide, we have some recommendations. For example, once of the outliers have been identified, they can be removed. This is done using combination of method and domain expertise. And always check that your identifier outliers are really outliers. With the help of artificial intelligence, we can get all of these elements, like missing data, phases prediction, core data prediction, petrophysical properties, bad data detection, data repairing, depth shifting, well correlation, geomechanical properties, and data normalization. Careful editing and conditioning of well data are two of the first steps in the seismic petrophysics workflow. We start to do data reconstruction in a poor quality areas of the whole with use of different structure of neural networks that you can see. In this example, we use a simple neural network, and in this example, we use a complex neural network. As you can see, if when we use a simple neural network, the reconstruction is better than we use a complex neural network. Simple learning algorithm and good training data always will be better than sophisticated algorithms. Now, seismic petrophysics is a term to use to describe the conversion of seismic data into meaningful petrophysical or reservoir descriptions, information such as porosity, lithology, or fluid content of the rocks. A typical petrophysics workflow can be summarized as follows. We have the petrophysics and the rock physics. The seismic petrophysics is the link between us, between this. So we can see in absurd way the example of what a rock physics modeling is. Imagine that you have the vegetables that there is our minerals. After that, we mixing. We add the sabor, the flavor. In this case, the porosity. And after that, we add the fluid. And in the subsurface, we take care of breaking down all these ingredients and knowing their elastic behavior. Velocity is a function of elastic modeling and density. The hardest component to characterize is the pore space geometry, yet this controls almost everything we are interested in. The empirical models are justified in this early stage of data editing because many other parameters necessary in advanced physics modeling are not yet determined. Okay, in this slide, we can see all the models that we have in rock physics. First of all, we have the empirical law, the bounds, and the effective medium models. We must to determine the rock metrics, dry rock, and saturated rock. Uh, like I said, um, if we use empirical laws can also be used to correct all outliers. Bounds, these rock physics bounds are only used to average mineral and fluids. And finally, we have the effective medium models, granular models, and inclusion models. This model we use in our case. This model requires some assumption of the microstructure of the rock. In this slide, we can see all the questions that we need for build our rock physics model. And also we have the elastic properties. For example, we have the Young modulus, the Poisson ratio, the Boyd modulus, and shear modulus. Okay, so far we know the difference between artificial intelligence and, say, seismic petrophysics. So we use each of these elements to obtain our petrophysical evaluation. In our case, the inputs were 10 wells with compressional and shear velocity, also with the density. Uh, all these wells in the same reservoir, in our carbonate reservoir. Like I said in the beginning, we must found the natural fracture with the acoustic impedance. After the formation evaluation, we run an inclusion model, and we can see the modeling of the elastic properties in the reservoir. Uh, like if you see, we have the prediction p velocity over the original one. And in this part, we have the original elastic properties and the elastic properties model. As you can see there, we have a good separation when we use an inclusion model, in this case for found or different bases. Acoustic impedance were classified into 4 phases, which were uh, low clay and high clay carbonate, the brittle carbonate, and the shale. As you can see, we obtain our fractures, our natural fracture with this phase, with these phases. Maybe, perhaps you are wondering what will happen if I use artificial intelligence and rock physics model to construct uh, the S velocity. Well, we did that, and this is the the answer. As you can see, we use a rock physics model, an artificial intelligence, and polynomial method to construct our S velocity. Observing the elastic properties, there is a lag in the model reconstructed by artificial intelligence. This is the use of artificial intelligence. Now, with the dendrograms, we show you the difference of use artificial intelligence instead of rock physics model. As you can see, we have a better control if we use only rock physics modeling to construct our S velocity. There is the importance to use rock physics modeling instead of artificial intelligence. This is one of the risk of use artificial intelligence instead of rock physics modeling. Um, Finally, we have the conclusions. In forward modeling, we start with a geologic model on the subsurface, which is modified to reflect the information contained in both well and seismic data. The well logs provide velocity and density data, as well as the vertical control we need to define formation depth. The seismic data, on the other hand, give us lateral control. We use this control to develop a preliminary model, which includes the number of interfaces, their depth, interval geometries, interval velocities, and interval densities. In general, forward modeling is used to determine the seismic response due to stratigraphy, structural, and hydrocarbon effects across a field. This is accomplished with an acoustic impedance log generated from sonic and density data. From this, we generate a synthetic seismogram tied to the original seismic data. Remember, if the two data are similar, then we have our solution. If the observed original seismic data and model the trace data are not similar, we modify our geological model, synthetic seismogram, and produce a new geological model output. We continue this interactive process until we produce a good match between the two datasets, synthetic seismogram and real seismic data. Hence the importance of having reliable data. And thanks for your attention. Thank you very much.
Lucinda, thank you. That was very interesting. And we can see that you put a lot of money into designing your presentation. There was a lot of love into it. So we really appreciate it. So before we move on to the question and answer session, I want to give you this acknowledgement. We want to thank you for the great work that you did and the time that you put into this, for having a part in this international forum, given the lecture. So on behalf of Francisco Javier Flamenco Lopez, who is the president of the local Mexico SPE section, receive this award that we will give you virtually. And thank you again for your participation. Now we're going to move on to the question and answer session. And I'm going to start on this with the beginning. So I'm going to start with Harshel. So Harshel, you had a very interesting presentation and we had a lot of questions from it. So it seems like you touched some good points, of course. So the first question is from Rafael Vargas, and it is, how do you model the condensate flux at perforation level, since that affects recovery?
Right. So what Rafael is basically referring to is condensate banking, and I feel that I'm also in the same position to ask questions. But yes, condensate banking is troublesome, especially with the gas condensates and the carbonate reservoirs, especially because you have lower porosities compared to typical sandstone reservoirs. And this can be overcome to an extent. I'm not saying it's basically 100% efficient. If you achieve this, you'll be able to capture in your modeling condensate banking, but you could try and have the best possible rock typing and also the rel perms that are associated with those rock types. So the more rock types you have in your model, and especially with the wider range of poroperms relationships that you have, the better it would be. It will not give you the perfect, or you will not be able to overcome the problem for 100%, but at least you will have some sort of better control over your condensate banking. But the condensate bank, you could also try to see from your pressure tangent analysis. There are methods where if you have high resolution gauges, you could figure out what is the external radius of your condensate bank. Sophisticated softwares could give you that as well. So you may try and figure out a way to incorporate that PTA result into the reservoir models for simulation and use that as a history match parameter if you can. I hope I answered the question.
Thank you. That was very good. Okay, so next question. This is from Efraín Acosta. He has two questions. So the first is, what is the maximum surface injection pressure recorded?
Right. So for the presentation which I had, the phase 1 and phase 2, we did 1000 psi, 1050 psi at the surface, and what we have ongoing now in the field is around 3000 psi. But that again depends on how much gas you are injecting into the wells. So it depends. If you are at the 100% capacity or volumetric capacity of your compressors, then it would be 3000 psi. And it also depends on the back pressure that you face from the wells. So right now it's lesser than that, but it's much higher than 1000 psi.
Thank you. And his last question, not for you, but Efrain's, is regarding the gas composition. Was it determined before or after compression?
No, this was done when we were injecting. So what we did was, before we planned to start injecting, we did composition samples, like 4 or 5 of them at least, and we spaced it out like over a few days, so we know we covered a wide spectrum when the wells were producing. So we wanted to create a benchmark of what was the scenario before the injection actually happened for the first time ever in the field life. So we want to be in a position where we had all the data sets that were required to perform any sort of analysis going forward. So that was done before. And while we were injecting, we were also collecting samples, typically once a day. And when we were producing, we were definitely collecting samples from all the wells. So 2 wells which were on production, from the wellhead, we were taking samples every day, and we were pushing to be taken for those samples to be taken at typically the same time, because we want your wellhead conditions in terms of ambient temperatures and everything to be very similar. And we were also taking samples at the separator where the wells were flowing into. So we had a dedicated separator, like a test separator, which was dedicated only for these wells. And we were taking samples from there as well. So we have an in-house facility where we just capture these samples and we would do the analysis in-house.
Thank you, Harshal. Okay, so final question, and this is from Alfredo Morales. Is it possible to apply continuous injection systems?
Can the question be elaborated a bit more, if that's possible?
Okay, let me see if I can translate straight from Spanish. Is it possible to migrate to continuous injection systems on arrays?
Right. Okay, I'm not sure. Okay, arrays. I believe this might be a question for Hannah probably, but let me see if I can tackle it from what my presentation was about. So yes, you could have continuous injection. So what we have now done is that we have dedicated injecting wells, and we now also have dedicated producing wells. So 2 of the wells are now only injecting, and 2 of them wells only producing. So what we are basically doing is performing a sweep. So we try to push the condensate or the hydrocarbons away from these injectors and push it towards the producer. So when they produce, you try to make sure that they are a bit more richer. So because what we have found is using huff and puff, so you inject, let's say, X volume of gas in each well, and you would have to produce quite a lot of volume back to get that condensate again. So you will not go back to your initial GORs or CGRs numbers. So it's best if you try to do sweep, but again, this is not not a one strategy fits all. So you'll have to see what fits for your reservoir, but this is what works for us at this point.
Thank you. Sorry if there was a confusion, but I think you did good. You did tackle it on your side.
All right. Thank you.
Thank you. Okay, so that's all the questions we have for you. Thank you very much. Please do not leave. We still want to thank you again. Okay.
Yeah, if anyone comes up more, I'm still here to tackle the questions. It's fine.
Great. Okay, so now we're going to move on to Hannah. So Hannah, we also have several questions for you, and we're going to start from a question from Jose Luis Pashbush. What is the wettability of the karstic reservoir, and how was it determined?
Yeah. Okay. So, well, the wettability of the Karstified reservoir, that's a very good question. Actually, well, the reservoir in general was intermediate wet, as it is a carbonate reservoir in here. And from a lab analysis, of course, we have obtained its wettability. As I told you before, we didn't have valid lab samples from the Karstified field, but in this case, actually, let's say it's not a very critical matter, the wettability of the karst, as they act as channels, as the conducts. So in this case, as you've seen from the relative permeability curve, it was more than oil wet KREL, but yeah, it wasn't that relevant, let's say, the wettability of the karst itself.
Thank you. Okay, so next question. This is from Mohammed. Is a negative Curie exponent physically possible for a natural refractory reservoir?
Yeah, well, yeah, that's a good question too. Actually, first of all, here it is a karstified reservoir. we didn't have even fractures in this specific reservoir. Is it possible physically? We're speaking about a micro phenomenon that combined together bring to a macro phenomenon. So I think that it was possible in this specific case. Yeah.
Yeah, that was a tricky one.
Yeah.
Okay, so this is from Gustavo. First of all, he wants to thank you for your excellent presentation. And his question is, you introduced an additional SATNUM region for karstified areas that will use the upscale relative permeability according to water saturation. What about saturation height functions, such as water oil capillary pressure according to water saturation? What approach did you use for karstified regions to match the oil niche in place? So I think that's
Yeah.
two, right?
Yeah, well, first of all, for what concerns the PC, the capillary pressure curves, here for the initialization of this model, we have used the initial water saturation itself as we had it directly from the geological model, and it was quite valid. For the PCs that we've used within the KREL, let's say it wasn't of a relevant importance, since it wasn't used for the calculation. How did we match the oil in place? Well, first of all, the geological model was matched itself. It is a field with, if I remember well, maybe 60 years of production. So let's say that the oil in place wasn't one of the more important parameters to match. It was already matched in this case. I hope I answered all your questions.
I think so. Thank you. If not, I'm sure they'll let us know. So I think it was good. Thank you. Okay, so this is a question from Fernando Flores. I'm going to try and do my best. It says, according to your experience in karst reservoirs, it looks like reservoir drawdowns will not affect the water production mechanisms as it would in a sandstone reservoir. Is that so? And if it is, can a karst-type reservoir reproduce at high rates?
Ah, okay. No, I didn't see this one. Okay, so is it? Sorry, I'm gonna just read it again. Looks like drawdown. Okay. No, actually, producing from karst at a certain point it doesn't become beneficial at all, especially when you start producing water. If this is your question, if I understood it well. Yeah, of course, we're not speaking about a sandstone in this case. It doesn't, the mechanism, the production mechanism is not the same, but karst act as a conduit or as a channel. At a certain point, the water production becomes really cyclic. So if you're injecting, for example, you're producing straight away. So the best case in this case would be to produce it as much as you could and then to abandon it and not, you have to avoid, let's say, karstified levels if you see any. That's why also the study with the prediction of karst location was of quite importance in order to avoid, let's say, specific levels where possible. I'm not sure I answered this one, but let me know.
Okay, let's hope so. I think it did. It was a complicated one. Good. Okay, well, thank you, Hannah. For now, that would be all the questions we have for you, but please do hang around. And oh yeah, Fernando Flores says it was nicely answered, so thank you. That was great. Okay, we're now going to move on to our final speaker, Luis Aindel. We're going to start with a comment from Rafael Vargas. He first wants to congratulate you for your presentation. It was excellent, and he thinks it'll be quite helpful processing the great amount of information that we have to deal with every day, and will help us to identify opportunities to maximize recovery. So his question is, sorry, do you think these technologies should be applied to the specialties of reservoir production and drilling?
Yes, I think so, but we must to have some rules when we use kind of artificial intelligence.
Okay, thank you. We're going to move on to the next one. This is from Jorge Rios. How do you control the difference, the scale difference in between seismic and petrophysical information?
We control these scales with the seismic inversion. That's all.
Good, straight to the point. Thank you. Okay,
Yeah.
and good. No, that's good. It's always good to be efficient. And finally, we have a question from Gabriela Garcia. How do you minimize the risk of using artificial intelligence?
Okay, for simplicity purpose, our input will have a binary value of 0 or 1. This technical defines in a perception as neural network preliminary leverage six-mode neurons, which represent values from negative infinity to positive infinity. This distinction is important since most real-world problems are non-linear, so we need values which reduce how much influence any single input can have on the outcome. That is.
Thank you. That was very insightful. And it's a good explanation on how to do that. We appreciate that. Heina, I think Gustavo agreed with your answer, and well, he left you a nice message on the chat if you want to see that. For now, that will be all for our question and answer session. We are very thankful. We are thrilled to see all the support and the interaction that you had. Now we're going to conclude this event, thanking everyone that participated. I want to inform you that we had a peak attendance of 183 connected devices. So that's a very, very good attendance. It's actually a little bit more. We know that some of them were sharing screens. Also, for those of you who do belong to the SPE, remember that you have 6 free downloads from the One Petro website. So some of the literature that you saw today on the lectures can be downloaded for free. It comes with your membership. I'm going to say that in Spanish again. Muchas gracias por todo el apoyo, la interacción que tuvieron, el interés y su tiempo de estar aquí. Queremos también recordarles que si ustedes son miembros activos de SPE, el sitio web One Petro ofrece 6 descargas gratuitas al año, así que la literatura que vieron el día de hoy incluso podrían descargarla sin costo alguno. Now I'm gonna give the opportunity to the chairperson of the young professionals so that he will give us the concluding words. Again, thank you, and that will be all for my part. Alfonso, you have the microphone.
Thank you very much, Maria. Hello, everyone. I hope you have enjoyed the presentations of this international specialist. All the activities that are prepared in the SPE Mexico section are to improve all members' technical and cultural background. So please share a virtual applause for our lecturers and to our moderator to thank for their effort and in hosting and the quality of the presentations. This is the first time that we make this kind of international forum. I am convinced that we will have more reach with more sections and further collaborations. As Lolis Maria said a few minutes ago, the meeting has an attendance of more than 183 people, some of them in meeting rooms, and it's 12:24 in local time in Mexico. And the name of the Young Professional Commission of the SPE Mexico section, we thank you for all your participation, and we invite you to turn on your cameras and microphones, please. All of you, if you want, turn on your cameras. I want to thank to Harshil, Hannah, Luis. Your presentation was very, very technical. That is that we expect for the Mexico section and Young Professional Commission. So it's a really pleasure to have you here today. Thank you. I know that the difference of the time, sometimes we cannot have a lot of participations, but this is the first one, and we appreciate all of you, all of your participations. So at the 3, we will say, I am SPE. You got it? Turn on your microphones, please. At the 3, I am SPE. 1, 2, 3. I am SPE.
I am SPE.
Excellent. Again. 1, 2, 3.
I am
SPE.
Excellent. Thank you very much. So you will
Thank
have
you.
the diplomas. I will send you the email. Thank you again, and we hope to see you soon in virtual way and in some of the SPE events. Thank you very much, María. Nuevamente muchas gracias. Muchas gracias a todos por su participación y por su asistencia. Javier.